This podcast is going to focus on bonding basics, which is all of Chapter 8. It's time to stick those atoms and ions together. So let's start off with ionic bonding. So to understand how an ionic bond forms, let's look at the reason why it forms. First off, we learned that when you have sodium, the ionization energy is 495 kilojoules per mole. That's how much energy it takes to remove electrons. And then if you look at chlorine, if you give electrons to chlorine, it actually releases energy. But when you add up the energy, the net energy for losing an electron from sodium and gaining an electron for chlorine is not actually exothermic, not in the way that we see it when we actually combine gaseous chlorine and sodium together. It's extraordinarily exothermic, but those numbers don't really explain why. So there's a third piece to the puzzle, which is called lattice energy. So what happens is that when these ions come closer together, what is as yet unaccounted for is the electrostatic attraction between the newly formed sodium cation and the chloride anion. So it's called lattice energy, the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. The energy associated with this interaction is governed by something called Coulomb's law, which is basically, you'll see you have Q1, let me move my pointer near here, Q1 times Q2. So the greater the difference the charge, because this is on the top of the equation, the greater the energy, lattice energy is. And the smaller the distance between the bonds, the greater the lattice energy as well. So when they're really close, it's much more exothermic, and then if they have great charges, much more exothermic in terms of its lattice energy. So lattice energy increases therefore with the charge of the ions, as you can see as we move down. Li has a positive charge, fluorine -1 charge, and then as you move over to magnesium and chlorine, magnesium has a positive 2 charge, and you can see its difference. And as you move down, you obviously have differences in lattice energy. It also increases with decreasing size of the ions. Moving on. This also explains the phenomena called the octet rule. And the octet rule is essentially that metals tend to stop losing electrons once they get that noble gas electron configuration, which is why in your first year chemistry course you always had your chemistry teacher saying they always want to look like noble gases. Well, they don't want to look like a noble gas. It's just energy favorable for them to look like a noble gas. That's the big difference between it. Covalent bond is different. You're obviously sharing electrons. And there are several charge forces going around. We call these electrostatic interactions in these bonds. And you have the force of attraction between the electrons and the nuclei. So if you have the nucleus and electron, you've got that attraction right there. Then you have the repulsion between the two nuclei of the atoms that are coming together. And then, of course, you have repulsion between the two electrons as well when they're coming together. So there's a lot of different forces. Although the atoms often form compounds by sharing electrons, they don't usually share them equally. When they don't share them equally, like this hydrogen fluoride right here, we call it a polar bond because the fluorine's pulling the electrons closer to it. And if I have two fluorines and they're identical to each other, you get a non-polar bond. So, moving on. Electronegativity is, of course, that measure of how much they pull electrons together. Electronegativity obviously increases as you go left to right and from bottom to top. When two atoms share electrons unequally, we call it a dipole. And that's when electrons are moving towards one side, not the other. We actually have a formula for it, and it's based on charge, and it's also based on the distance between the two, and we call it a dipole moment. Moving on. We don't really need to know what it's measured in. Polar covalent bonds. The greater the difference in electronegativity, the more polar the bond is. We use a scale for measuring electronegativity, and you can measure that electronegativity difference by subtracting the electronegativity of one atom from the other. So if you take chlorine minus the electronegativity of hydrogen, you can see the electronegativity difference. So the greater the electronegativity difference, the more polar the bond is. Alright, Lewis structures are how we show the molecules with the electrons, the bonding electrons, and the non-bonding electrons. One of the ways that we write the Lewis structures, this is the way the book does it, is first you add up all the valence electrons. And don't forget, if there's a charge, you want to add an electron for each negative charge that's on it. If it's a cation, you obviously subtract it. Moving on. Then you want to put the central atom on as the least electronegative element. Very often it's the first written in the formula. So this one would be PCl3, P would be your center atom. Draw the bonds, single bonds. Keep track of all the electrons you've used. So there's 3 bonds, so that's a total of 6 electrons. Each stick is 2 electrons. So now we have 20 electrons left to fill in. Start by filling them in on the outside. You've got 2 left, and then fill them in on the inside. You should have 0 valence electrons left once you've done this. If you run out of electrons before the central atom has an octet, go ahead and move some of those pairs to the center. And when you move them to the pair, you have multiple bonds until everyone has an octet. Don't forget that means 8 valence electrons around each of them. Except for hydrogen. Hydrogen is an exception. So carbon, I'm going to count each stick next to it. I have 1, 2, 3, 4 sticks. That's each stick is 2 electrons, so that's 8 valence electrons. That's the octet. For nitrogen, it's got a pair here and then 3 sticks. Each stick is 2 electrons, so 2, 4, 6, 8. Nitrogen has an octet. Then there's this thing called formal charges. Formal charges allow you to predict what structure is best. For each atom, count the electrons in lone pairs and halve the electrons it shares with other atoms. I like to do it this way. For me to figure out the formal charge on this oxygen I'm circling, I just count out 2, 4, and then half each of these 6. So 1 and 2. So 2, 4, 5, 6. So it has 6 valence electrons, and 6 that I just counted around it. So its formal charge is 0. Let's compare it with this structure on the left. So I know oxygen has 6 valence electrons, so it's 6. Let me count the ones around it, so it's 2, 4, 6, 7. So its formal charge is -1. Formal charges allow you to identify which molecule is the best structure representing it. So whenever you reduce the formal charge, that's usually the better structure. So the one on the left is the much more appropriate structure to describe carbon dioxide versus the one on the right. Now, moving on. The best, this is actually the same thing I just said. The best Lewis structure is the one with the fewest charges. Always put a negative charge on the most electronegative atom. That's also something that's very important as well. Here's a Lewis structure for ozone. Ozone has resonance, which means that the oxygen bonds are at the same length, and each of them have a negative half charge. So the Lewis structure can't accurately depict a molecule like ozone because the electrons are bouncing back and forth between both of the bonds. So we use multiple resonance structures to describe this type of a molecule. This is the book analogy, which is basically if you combine blue and yellow, it describes the more accurate structure of the molecule. Blue and yellow more accurately is described as green, that's what we see. And the 2 resonance structures really describe what ozone looks like. Alright, in truth though, the electrons that form the second CO in these molecules, the second CO bond and the double bond, do not always sit between that carbon and oxygen but can move around. You can see the double bonds here, sometimes it's over there. They can bounce back and forth, and that's an example of resonance. They're not localized. We actually refer to that as the bonds being delocalized. This double bond that I'm highlighting with my mouse pointer is not always there in that particular location. Alright, resonance structures can occur between molecules like benzene. Benzene has resonance amongst all its carbon atoms. And these are the 2 resonance structures, so we actually draw a circle showing that the electrons are delocalized amongst all the carbons, all those double bonds. It is commonly depicted as a hexagon because we like to not draw all the hydrogens. We're typically kind of lazy as chemists. Alright, moving on. There are actually exceptions to the octet rule. There are 3 types of ions or molecules that don't follow the octet rule. First one is ions or molecules with an odd number of electrons. Second is ions or molecules with less than an octet. And the third one is ions or molecules with more than 8 valence electrons, an expanded octet. So let's go through them. Odd number of electrons. It's usually rare, and it's unstable and typically very reactive. But there are ions and molecules with an odd number of electrons. Let's take, for example, this one, Bf3. Giving boron a filled octet places a negative charge in the boron and a positive charge in the fluorine. This would not be an accurate picture of the distribution of electrons in boron because, of course, the negative charges should reside around the fluorine, not the boron. Therefore, structures that put a double bond between boron and fluorine are much less important than the one that leaves boron with only 6 valence electrons, with only 3 bonds. This one's much more important than the other ones, because if you look at the formal charges for this structure, it makes a lot more sense because the negative charges are on the fluorines and not on boron. So this is when it has fewer than 8 electrons. Basically, what you want to learn from this is that if you're filling the octet of the central atom and it results with a negative charge in the central atom and a positive charge in the more electronegative outer atom, don't fill the octet. Leave it in as only 6 electrons for boron, and don't try and complete its octet like the ones on the right. Alright, there are exceptions where you have a central atom that has more than 8 electrons around it. The only way PCl5 can exist is if phosphorus has 10 electrons around it. It is allowed to expand its bonds into the d orbital. It's got the d orbitals actually are participating in the bonding. Even though we can draw a Lewis structure for the phosphate ion that has only 8 electrons around the central phosphorus, the better structure actually can put a double bond between phosphorus and one of the oxygens. So the one on the right makes a lot more sense in terms of how we draw out the formal charges as opposed to the one on the left. So we've actually expanded the number of electrons that are around phosphorus beyond the octet rule, and we have more than 8 electrons around it. This eliminates the charge on the phosphorus and the charge on one of the oxygens. So the rule is basically when you have a central atom and it's on the third row or below, and when you expand its octet, some of the formal charges actually work out better. Moving on, covalent bond strength. Simply, the more bonds, the stronger the bond. So we measure bond energy also by how much energy is required to break the bond. So when we do this, we call it bond enthalpy. The bond enthalpy for a chlorine-chlorine bond. The bond enthalpy for chlorine-chlorine is about 242 kilojoules per mole to actually break that bond. We have tables of these bond enthalpies. Now we can use all these average bond enthalpies are positive because whenever you break a bond it requires energy. Breaking bonds is endothermic. Energy has to go into it to break the bond. Forming bonds is exothermic. Energy is released. So note, these guys are average bond enthalpies, not absolute bond enthalpies. The CH bonds in methane will be a little bit different than the CH bonds in CHCl3. So don't forget, these are average bond enthalpies. It's really important to emphasize the average here. Alright, enthalpies of reaction. So there's another way to estimate the change in enthalpy for a reaction, and it's by using these average bond enthalpies. So we actually use this formula. It's very similar to Hess's law. What you do is you take all the bond enthalpies broken, you add them all up, and then you subtract that from all the bond enthalpies formed. This makes sense in terms of positive and negatives. I actually like the preference of taking all the things that are broken and making them all positive, and then adding them to all the bonds formed. But when I'm forming bonds, that's energy being released, so make sure those values are negative. Because don't forget, this first value that I'm highlighting with my pointer plus the negative of the other one is the same as the first one minus the positive of the other. Moving on. So if I'm trying to find out the enthalpy of reaction for methane reacting with chlorine gas, what we have here is we have one CH bond and one ClCl bond, and one CCl bond and one HCl bond are formed. So this is the energy diagram that we have here, and that's how much energy is released in this particular reaction. We can also measure the average bond length for different bond types. Bond lengths change based on how many bonds are there. As the number of bonds between two atoms increases, the bond length decreases. So as you notice, you have triple bonds, it's a very short bond. If you have a single bond,